All right, guys, ready to start? Awesome. All right, welcome back for those of you who were not here last week. This week, we'll get right into it. No review this week. We have a special guest speaker, so go ahead and stand up. Dr. Joy. So this is my good friend that I've known for a long time because we went to Tulane University together. Joy was 1 year under me. And she also went to graduate school at Tulane. So we were in schooling together for a long time. She then came and worked at Intel, actually ended up working in the same area as I did. And then she decided to move on. She went and she worked at Cabot Microelectronics for 5 years, and then has recently left that position to become what her current title is. She is the Strategic Account Manager at Danippon Screen, informally known as DNS in the area, and they make semiconductor equipment that we buy and use at Intel. So she is here to talk to you about not only who she is and her work history, and again, feel free to ask her questions as you go, but she's here to actually talk to you about a problem that she solved by implementing what we talked about last week, which was, somebody remind me, what did we talk about last week? Engineering statistics, more specifically, process control, right? We talked about control charts. Joy used that to solve a problem, so she is the perfect expert to tell you about how that actually matters, what we talked about last week. So at this point, I'm going to turn it over to Dr. St. Dennis, and she's going to tell you all about it.
Awesome. We can loop back if you have questions on the jobs that I've had and how they fit together, but let me jump to my example of what you guys worked on together. In the last role that I had, I was responsible for the supply chain for the whole division of my company. So I had a team of 12 people that worked on all of our raw materials and trying to improve our raw materials to improve our end product so that when our customers used it, they saw even better performance. And so what we did was we took our customers' trend chart that had limits on it, so it was a control chart, up at the top, and we noticed that there was a period where their performance, I circled it in red, it's got the blue plus signs, wasn't as good as other times. So we focused on the area that was circled in red. Why were there fewer of the good points, so the ones that were on the bottom half of the chart, than there were during the time that there were a lot of plus signs above the line? So we went to our supplier and we looked at all of their material that they had shipped to us, and we had noticed that the good times, so when the customer performance was down in this area, the supplier's material was in this part. And we noticed that when the customer's performance was in the red circle, the supplier's material was above this line. So we used process control and control charts and statistics to take our customers' data, and then we processed it and looked at the charts and tied it to our supplier's chart, for which we turned their raw data into another control chart. And not all the industries in the world use the stuff that you talked about last week. It's kind of an advanced technique. So for some industries like semiconductors, for which Beaverton in Oregon and Hillsboro is pretty darn strong, it's something that people use every day. There are engineers that use process control charts and statistics every day. But for other industries, so think of bulk chemicals. So the chemicals that you see in rail trucks or rail cars, really large amounts of chemicals at the same time, they don't use process control systems and statistics on an everyday basis. So first we had to notice the trend in the customer, and then we had to tie it to a supplier chart, and then we had to convince them why process control systems are a good idea. So what we asked them to do is, this is where their limits were before. And we said, hey, you know what? When your product is within these control limits and you don't ship us this stuff, our customer is happy. How do we work with you to get all of your material into these lines so that our customer doesn't get any of the stuff outside of the lines. I'm simplifying it. It took 2.5 years, but with a lot of data and a lot of teaching them about the things that you learned last week in this class, we actually were able to take the limits that were quite wide, that were actually out here, and we tightened them to here with new limits. And when we actually taught our supplier about control limits and statistics and why these things matter, we were actually able to take our customer's performance and eliminate all that stuff in the red circle. And why that matters is because when data is up in that red circle, that actually was problematic material for our customer. So they actually had to take those chips and throw them in the trash. They didn't work. So if you think of just that stuff in the red circle, that was millions and millions of dollars of inventory that our customer had to put in the garbage. And so I know that sometimes our supplier was like, dude, Joy, this doesn't matter. Why would I want to make this change? But even just a little signal from one parameter in a raw material that it has tons and tons of it made to our product and then to my customer took a simple thing and made it to be $10 million of improvement at the end of the line. And so what you looked at last week is really important, and not only using it when you look at your data, but also for your future customers or your future suppliers. Analyzing your data with the skills that you looked at last week actually is hugely important. And what you learned was a different way to look at data than a lot of people and a lot of engineers in a lot of industries ever use. So it's incredibly important, and you guys are going to be advocates for this at your future companies as to why using statistics and process control is hugely important. And it's something that I still use almost every single day. So I know that you talked about it last week, but it's awesome, and companies around here use it very regularly. But what I found is that around the world and in a lot of engineering places, it's not used all that often.
Yep, that's what I told them last week. Because
if
they now that they're masters, they can all come work for me, right? So
yeah. And once it becomes part of something that you look at and it becomes part of your DNA, it's something that you will advocate for and champion to all kinds of people that don't know what it is.
All right. Well, thank you. At this point, does anybody have any questions for Dr. St. Dennis? None? It's an awful quiet class.
Well, I will...
All right, so let me ask you the question. I'll get it started because we always ask everybody who comes here the same question. So if you were sitting in their chair, or I guess when you were them, what would you wish you knew then that you know now?
That it's all going to turn out okay. Sometimes along the way when I was a junior, sophomore, or a senior in high school, classes felt hard. And some of them were harder, and some of them were easier for me. Physics, I had a hard time with physics, but chemistry, I loved it, and math, I loved it. But for some reason, I had a hard time with physics. And it would have been really great if I had known that it was all going to work out just fine, and that if I kept at it and I kept working, even if I got a B in a class, or even in college if I got a C+ on a test and I broke my heart, it was all going to be fine. I was going to excel in the classes that I was passionate about, and that passion in those classes was going to keep me going through the ones that didn't come so easily to me. And I know that if you guys are in this class, you are adept students, and so stuff probably comes easier for you than it did for me, but I kept my head down and I didn't give up. And so if I could give you one piece, I would say that when stuff gets hard, and it will at some point, whether it's one class or it's one teacher or one project or one theorem that you're calculating or one Laplace transform that you are so tired of that you could throw it down a well, don't give up, because it will get better, and you will look back on it 10 years later and you will be like, dude, that was hard and I got through it. I'm stronger for it, and now stuff doesn't scare me. So whatever you got, whatever problem you have, bring it, because I'm tough and I'm not going to back down. And I think I hired a lot of people in my last job, and what I would look at or look for when I hired people was just tenacity. I didn't I didn't really look at their grade point average, right? You get above a 3.2, you even get above a 3.0, and I know that you can hack it. What I looked for was people that were passionate, would roll up their sleeves, would dive into a problem, and wouldn't back down, wouldn't be afraid at the first sign of things getting hard. Because engineering's hard, right? There's a reason why these problems need to be solved, right? I talked about one tiny supplier in the middle of Arkansas who, when I told them about process control systems, was like, Ms. Choi, we have no idea what you're saying, but if you ask us to, we will figure it out. All the way to 10, 12, $15 million for Intel in improved yields and things like that. So it's not easy. If it was easy, everybody would do it. But I promise you there's a solution. There's a root cause at the end of the problem. When I worked with Andrew back in the day, there was a particular problem that Andrew worked on for 18 months. And
are you talking tungsten stringers?
I sure am.
Yeah.
And it wasn't easy, but he kept at it. And eventually that problem was resolved.
Sort of.
Sort of. But exactly. So don't give up, even when it gets hard, and look to each other as support systems. You guys are your best network because you understand how hard it is. And there are some classes that are easier for some, and there are some classes that are a little bit easier for others just because of the way that our brain chemistries are drawn to certain problems. Work together and realize that you're not each other's competition, because the more of you that there are, the stronger your classes are because you're working together. Sorry, that was a lot longer of an answer than you probably expected.
Nope,
but
good answer. So I'm going to go ahead and speak up for some of the young ladies in the class. So you are the first female professional engineer who we've had come
Hey!
Or I should use the words professional engineer very carefully, because
Yes.
you're not a PE
I do not have
right?
my PE license.
We don't want the state of Oregon to fine anybody, right?
Yeah.
So you are the first professional in the engineering field of the female persuasion. So
Yes.
how do you feel that being a female has affected you through not only your schooling, but also your early career? Because obviously you're established and you're doing very well right now, right?
I would say that being a female was never a hindrance. What was a hindrance for me was my age. I had to work a lot harder so I left Intel to go work for a startup. And I was really excited about the startup, and it was fantastic. And if in your career you ever have the chance to go work for a startup, give it a second look, right? It's a little bit of a risk. They're not all successful, but the way that you learn to work together with people is exceptional. So I went to go work for a startup, and about a year and a half after I went there, we were bought. And it's really good. That's a really good thing, right? Because the world and the area that you're in values what you're doing, and they want what you're working on. So we were bought. It was fantastic. But what I realized when I went there is that I had a whole new group of people that were noticing that I was barely 30, and I was in a position of some influence and authority. So I had to restart again, getting my street cred from a whole bunch of people who didn't really want to give me street cred because of my age. So it actually I have yet to see something where my gender or the other diverse things that make me a diverse person have been that much of a hindrance, except for my age. And how do I solve it? I ignore their prejudice for my age, and I start talking with ideas and data and statistics and conclusions, and I politely but firmly advocate for the path that I see forward, and I go after it. And actually, that's why I just took my current role. So I've been a strictly technical engineer up until January, when I moved to a new company, because they offered me a position in the business unit. And what I had found in my technical roles was that I could make all of the engineering solutions that I thought were super awesome, but in the environments that I was in, the decisions were made by the business people. And I was like, okay, I got to figure out what those business people are doing, and I got to go figure out how to make the decisions, how I get to make the decisions for the things that I want. So I've taken a bit of a career pivot in the last couple of months, going from a strictly technical engineering path to pivoting into the business team. I'm the only PhD in our organization that is in the business team now. But it's actually interesting because I walk in the door and it's already like, oh, Joyson has a PhD. I'm sorry, our company is a Japanese company, and so I am known at the office as Joyson. So it actually is not a step back. It's actually allowed me to get street cred from my sales peers even faster. And I'm going to be so bold to say that my customer, I think, trusts me 2% more because I have a background in engineering and I'm not just a salesperson.
Excellent. Well, I think with that, we'll get into the lecture, but Joy, thank you, or Dr. St. Dennis, thank you very much for coming. Any last minute questions before we, she's going to hang out and help us with this because tonight, so thank you, Joy.
Yeah, so thanks for having me. It's always nice to see you guys. And like I said, don't give up. I know it gets hard in high school and in college and if you go to grad school, but we need people like you to keep solving problems. So please stick with it, as hard as it gets. Okay.
All right, so tonight we are talking about material balances. So material balances is the fundamental class that all chemical engineers and environmental engineers, and am I missing anybody else? Well,
Maybe
I mean, we
cities.
talked about chemical has nuclear and all sorts of spin-offs of that, right? But this is a fundamental class. It is the class you take first semester of your sophomore year. We're right along with thermodynamics as your back-breaking intro to engineering class, right? So, Joy, like I said, Dr. St. Dennis is going to help me teach because we both are pros at material balances. So, actually, before I go to the next slide, let me ask a question. What is a process? What's a process? Something that you go through to do something. Nailed it on the head, right? So it's either a process that you go through, you get up in the morning, you brush your teeth, you get dressed, you go to school, or it's we do A to do B to do C to do D to make a manufacturable product, right? So what material balances is worried about is processes, right? So process is any series of action steps or operations achieved in a particular order to achieve a particular objective. So in basic terms, it's an organized method of doing something, right? Makes sense. In fact, you actually said it much better than I did, okay? So as engineers, though, we're not concerned with you getting up in the morning and all that, right? What we're concerned about are industrial processes, right? Processes that take something and make something else with it, right? We take small parts and make it into something usable, or we take base chemicals, mix them together, and we have an outward product like gasoline or something like that, right? So such a process can be small scale, like we're going to be doing tonight for our lab in a benchtop experiment, or it could be large scale, like what we do at Intel, or at Woodlike Refinery down in Texas, making gas that they send across the country, okay? So a process flow is very simply the sequential order in which we do our process, right? So let's look at this hypothetical process I have here of a bakery that makes cookies, right? I'm sure somebody in here has baked cookies before, right? Let's see, I have a theme, right? Last week was pancakes, this week's cookies, right? But you take all your ingredients, you mix them together, you form your cookies into little things. Sometimes you spoon them out, maybe you put them in certain shapes to make them look cute at Christmas. Then you're gonna throw them in the oven and bake them, and what's your output is cookies. So what goes in, we call an input, and what would that be in our case? What would our input be? The ingredients, right? And our output is what? Cookies, right? So the process flow itself is going to be mixing ingredients, shaping dough, and baking, right? It's a 3-step process, okay? Any questions on that? Pretty straightforward, right? Good. All right, and this is where we get to the inputs and outputs, which are actually called feeds and products. And the reason that it's called a feed and product is because at a very basic level, each and every one of those steps, so I'll actually go back to the previous slide. Each and every one of these steps has a feed or has an input as well as an output, right? So what is the output of, what's the input of mixing? That one's easy. Ingredients. What's the output of mixing? Dough, unformed dough, right? Yeah, you nailed it. And then the next step has an input of what? Unformed dough, and an output of what? Formed dough, right? And so on, right? So we call them a feed and a product. And of course, the overall process itself can have, right, if you look at the whole process itself of making cookies, it has ingredients to cookies, but each individual step can have feed and product as well, right? So if we wanted to draw our process, we're going to use what we call a block flow diagram, right? This should look very fundamentally simple or similar to you guys to a lot of other stuff we've looked at, right? We use arrows and boxes because who wants to sit and draw eggs and bowls and whisks, right? So we're going to take some amount per hour of our bulk ingredients, and we're going to feed it to our mixer. Out of our mixer comes 1.2 kilograms per hour of dough. And then out of our shaper comes 12 balls of dough per hour. And then out of that comes 12 cookies per hour. So who wants to take a stab at this and skip ahead and explain to me why 1.2 goes into the mixer and 1.2 goes out of the mixer, even though it's something different? Because the total amount is the same, right? So this is probably the thing that you guys are sick and tired of me talking about all year, right? What goes in must come out. Otherwise, what happens?
Accumulation.
We either lose something or what else happens? Blows up, right? Accumulation, as we said, accumulation, right? So what goes in, remind me again? Come out. All right, so you guys are now officially materials balance pros. Okay, you got it. That is all you need to know. Class is done. All right, so there's more to it than that. So if you could please go to page 38 in your handbook, and I double checked it today, the number is correct. So I would like you to please construct a block flow diagram for the following process, which converts chemical AB2, to create chemical product AB2 from reaction of its individual components A and B. So I'll go ahead and read the statement, but it's written there for you. Component A and component B are added to a mixer at molar flow rates of 100 moles per hour and 200 moles per hour respectively. The mixed stream is then fed to the reactor, where 1,000 watts of heat is added to initiate the reaction. The reactor product stream containing 80 moles of AB2, 20 moles of unreacted A, and 40 moles of unreacted B is then fed to a separator, where each component is completely separated. All right, so let's take 3 minutes and draw a block flow diagram. Okay, now remember, block flow diagram will have labels on the streams of how much is flowing between them. All right, so we're going to do this one together, and Dr. St. Dennis is actually going to...
I'm going to Vanna White.
Yep, she's going to Vanna White while we walk through it.
Someday she's going to retire and no one's going to know what that means anymore, but for now, let's go with it.
Fair enough.
All right, guys, what's my first step?
So what's the first thing we want to do? We want to draw our components. Okay, so what is the first component we have?
All right. Got a nice amount of A. I'm going to just go ahead and draw an arrow in there.
Yep. What does A go into? It goes into the mixer, right?
Okay.
What else goes into the mixer? Component B, very good. Oh, she's even drawn a CSTR. I love it.
Sorry.
I love it.
Old habits die hard.
I love it.
All right, I heard you guys say B. Anybody got a flow rate for me? Moles per hour, okay? Okay. All right.
All right, so what leaves our mixer? Do we have A and B leaving our mixer? Or do we have one single stream? One single stream. So Dustin, you said one single stream.
Okay, I got one stream.
Okay, and that stream is of what? How many moles per hour do we have in that stream? We have how many? Why 300? Okay, so we have how many moles of A are in that? And how many moles of B are in that? All right, so that stream, now has anything changed yet? There's been no chemical reaction yet, right? So that stream has 100 A in it and 200 B in it. Okay, so we're going to label that. And then where does that stream go into? It goes into the reactor, right? And that's where all our money is. That's where everything's going to happen. Sure. Yep. Very good. All right, now, so another thing goes into that reactor. What else goes into that reactor? 100 what? 100 watts per 100 watts of heat? And why is there no rate on that? Because watts is a rate. Nicely done, ma'am. 1,000 watts. Either way. All right, so then what leaves our reactor? So do they all leave in a bunch of streams? Or is it just one pipe? A bunch of streams? Are you sure? It's just one pipe, because we haven't separated them yet, right? So we just have one stream that goes into our separator, more than likely a distillation column. All right, so we have three things, right? Miss Joy did it correctly. It's AB2, A, and B are all the components in there. And then what do we do in our separator? We separate them. So now we have three separate streams. So what are we going to label that bottom stream with, Madison? A? Okay. I was going to say there's no right or wrong answer. You just got to pick one. Yep. All right, so A, B, and AB2. How much A do I have, Madison? 40?
20 of A. Okay. How about B? Okay. And what about AB2? 80?
All right. So we have completely drawn our block flow diagram, and now we as engineers can go back and solve that if we have to, right? Because this is a completely 100% labeled, right? Do we have any unknowns up here? The answer is no. We know absolutely everything about this. But where you, as the engineers, are going to end up is you're going to know what's going into your process, and you're going to know what's coming out of your process. But you're going to have to go be able to determine what's in the middle and what's happening so that you can optimize it. Now I have one more trick question for you. How many moles are going into our process again? How many moles are coming out of my process? What's that? Is it 300? No. Why is it not 300? Because it's reacted. Very good, right? So that's where the trick comes in with the chemistry part, right? Is mass is conserved, but are moles conserved? And why is that? Because does AB2 weigh a heck of a lot more than A or B individually? Yes, it does, right? So 1 mole of AB2 weighs way more than 1 mole of one mole of A or 1 mole of B. All right, very nicely done. All right, give us just a sec here to roll this out. We're actually going to need this again, so let's throw it back here.
Watch your bag.
Oops, all right.
That's all right. Just leave it there. I don't have to go much farther. Oh.
I ran over your bag. All right. Perfect. All right, so we got that all figured out. So now I want you guys to consider a sink. Okay, just a normal sink. So if I turn on that faucet, it's going to flow water into our sink, right? And that drain is where the water comes out of the sink. So let me ask you a question then. What happens if the outlet flow is greater than the inlet flow? What's going to happen to our sink? What's that? It will never fill up. Okay, I agree with that. But what else is going to eventually happen to our sink? It's going to dry out. Right? You're exactly correct, right? So if our outlet is greater than inlet, what's eventually going to happen is it's going to drain completely. No water in our sink. Now, what happens if inlet is greater than outlet? It's going to flood? You think so? I agree, right? So our sink's going to overflow. But now what if we get to that exact sweet spot where outlet flow equals, we got a typo. What happens if we get to that sweet spot where outlet flow equals inlet flow? The answer is the level's going to stay exactly the same. Why would we as engineers, especially engineers concerned with material balances, want everything to stay the same? What's that? So we know what's happening, but it's also so that we can continue to operate that process indefinitely.
Just like you said, it's constant.
Okay? So this is a concept that we call, which is going to be your bread and butter if you're a chemical engineer, called steady state. Because as we all know, what happens if we throw way more into the front than we get out of the process? What's going to happen to inventory in our process? It's going to build up. And what happens if we're not feeding our process fast enough? It's going to dry up and we're not going to realize money, right? That's what I was getting yelled at work today, is not feeding something fast enough, okay? So we already covered this one, right? Law of conservation of mass. You guys are pros on this one. What goes in has to come out. We're all down with that one. So this brings us to the general balance equation, which we've seen something very similar for almost everything else we've talked about, right? What goes in minus what goes out minus what's generated minus what's consumed equals the accumulation in the system. Okay? So what are materials balances? Simply just the application of the law of mass balances to all of our processes. Okay? And again, we get back to mass in equals mass out. So what you're going to see is something similar to what we're looking at here, right? So if we consider this two-component mixing process, we have a stream of A and a stream of B, both entering our mixer, just like we had in our block flow example. They're going to mix, and they're going to leave in one outlet stream. So this is just a mixer. There's no chemical reaction happening here, and we have three unknowns, right? What's leaving our reactor? So how much mass, Benjamin, do I have leaving this reactor? Or sorry, this mixer, not reactor. How much mass do I have leaving this mixer? 400, and why is that? Correct, right? Does everybody agree with that? 400 total goes in. How much do I have to have coming out? Benjamin's 100% correct. We have to have 400 coming out. Now, here's the tricky part, right? What is the mass fraction of A? So XA is the mass fraction of A. Or actually, no, sorry, that's labeled in kilograms per hour. So how many kilograms per hour of A do I have coming out in that stream? How many, Rahul? 300. And how much B do I have coming out? Malika? 100, right? And now if we get to the mass fraction part, what is the mass fraction of A in that outlet stream? What's that? 75%. Very good, right? And how'd you get that? 300 divided 400, right? Component mass divided by total mass. Very good. And then, of course, we would have to have the other be 0.25 or 25%. And why is that? Because it has to add up to 100, right? Very good. So what you guys just did is you looked at this and you solved it. But let's look at it at a more fundamental level, because not everything's going to be simple enough to where you can just look at it and solve it. So what we're doing is we're setting up equations here. So you said, what Benjamin said is he said, well, the total mass coming out is equal to the mass going in. So he said A plus B equals MT, total mass, right? So that's one equation. The second equation you had was, in this case, it's not really an equation. It's just A equals A, right, on in and out, right? AN equals N out, A out, and BN equals B out. So what that gives us is three equations in this case. We have a total mass balance, we have a component A balance, and we have a component B balance, right? And again, in this case, it's very simple, but what you can end up doing is using variables, or using one equation to plug in and solve for the other equation. So let me ask you guys this from your math. If I have one unknown, how many equations do I need to solve for one unknown? How many? One is correct. If I have two unknowns, how many equations do I need to solve for two unknowns? Why is it two? Because there's two unknowns? No. But the reason is because what you can do, like if you have two unknowns, you can make one unknown in terms of the other unknown. Right? It's your systems of equations, right? You have to make one unknown in terms of the other unknown, and then you plug into the original equation, solve for the new unknown, and then back solve, right, to get them. Now you get into the tricky part where in this case we have three, and then you have to do one of those nasty matrix things, right, which everybody hates doing, but at least we have computers to do it for you, right? And so on. So if I have 20 unknowns, how many equations do I have to have? 20 equations. Very good.
And this actually is used in the real world. So for example, Andrew said that the company that I work for makes pieces of equipment. These pieces of equipment are like the size of a minivan. So it's not like something you use on your benchtop, right? We are measuring all of the chemicals that are going in, but because they are highly corrosive and acids and bases, we can't put a flow meter on the way out because it would eat through that flow meter faster than we could replace it. So we actually have to use mathematical models based off of material balances to calculate how much acid and base is going down the stream, because in the spirit of Oregon's Oregon and the world and being good environmental friendly partners to everyone, we want to make sure we're not putting too much down the stream. But we can't put a mass flow meter there, and we can't measure it, and we can't stand there with a pH probe making sure that everything is neutral. We've got to say, what's the worst case scenario, and know what's going in, what's coming out, and can we use a bunch of equations to say what's the worst it could be and what's the best that it could be. So this is real world stuff that people do and use, and when there's 20 equations, we're grateful for computer software that'll do it real time for us every 5 minutes, every 30 seconds, based on what's going in.
And you'll quickly find in college, if you're doing this, that there's a tipping point. If it's 3 unknowns, it's not worth building the computer program to solve for it. But if there's more than that, you want to build it.
Yep.
So, all right. So this brings us to different types of processes before we go into the actual nitty-gritty here. So a batch process is a process in which what we do is we're going to put all of our product in at the very beginning. We're going to mix it together, and we're going to let it sit and stew and do its thing. And then sometime later, we're going to come back and we're going to remove the product, and that will be, or remove the product, and that will be our end result. Right? So can anybody think of examples like that?
I was going to say distillation, but that would.
So distillation, interestingly, is both, right? So what we're doing tonight actually is a batch process distillation. Distillation, ideally, like the way they do it in industry, is actually continuous. So I have an example. I brew beer, right? So what I do is I take a big bucket and I throw all my ingredients in there, mix them all together. I do some heating, and then I come back about a month later, and my beer's done. All right, so that would be a batch process. I put everything in, I seal it up. Well, mostly seal it up because gas escapes, but you get the idea, right? So I seal it up, they come back later. That's a batch process.
We had an example of pickles up front.
Pickles. That's a good one. Yeah, pickling stuff. That's a great example. All right, so I'd like you to go to page 39 in your handbook, please. And this is a very simple example of a batch process. 2 oil-water mixtures are in separate tanks. The first mixture is 30% oil by weight, and the second mixture is 75% oil by weight. If 0.5 kilograms of the first mixture is mixed with 0.2 of the second mixture, what is the mass and composition of the final mixture? So just to give you a hint, right, what we're going to do is start with the total mass balance to find the mass of the final mixture. And then you're going to solve for each of the components. All right, so let's go ahead and go through this one together as well. All right, so how I did it was I started with N equals out. Should sound very familiar by now. We know that we have 0.5 in and 0.2 in, which equals how much in? 0.7. Right, so now we're going to use the oil component balance to find the amount of oil in the final mixture. Again, our equation is going to look like what? I'm looking for N equals out, right? So we're going to start with N equals out. And now we're going to do, remember, and this is why we put percents, right? That's what we talked about weeks ago. We always try to do our percents as decimals, right? So 0.3% or 0.3 times 0.5, which is the amount of oil, right? Because it's 0.3%, or sorry, it's 30% oil. 0.3 times the mass. That means that's how much oil is in there. 0.75 times 0.2, and that's going to equal 0.3 kilograms oil. So the weight percent of the oil, right, just as Dustin said for his solution earlier, is component divided by total. So that one is 42.9%. And then, of course, we didn't ask you to solve for it, but if I were to ask you right now to tell me how much of the water is in there, how much water would be in there? What's that? At 1 minus 0.429, right, which is how much? Roughly 57. Very good. All right, next is what we already talked about, or what Benjamin alluded to, is a continuous process. Now, continuous processes are where your money is at. Now, obviously, there are some things like brewing beer where you can't do a continuous process, right? But what we ideally want to do is get our factory up and running and keep it running for as long as possible, because there's a lot of money that's lost in startup, right? Charging lines, getting stuff where we want it, warming things up. So once we get it there, we want to keep it there as long as possible. So a continuous process, very simply, has a continual input, a continual output, and things happen in the middle. Does anybody have a good example of a continuous process in your everyday life? A motor? That's a very good example. Actually, that's a perfect example, right? That's exactly what I was trying to explain earlier, right? So what happens? Right? Well, your fuel efficiency stinks when you turn your car on, right? Until you get your carburetor warmed up, right? So you're gonna turn your car on, especially if it's cold out. That's why sometimes in the morning, right? Or when you turn your car on, you'll smell gas when you first turn your car on, right? Because your engine's not warmed up, it's not performing very efficiently. You're losing some of the gas that's burning, and then once your car gets warmed up, you're inputting gas, and you're getting go out of it, right? So it's a continuous process. You're putting air, you're putting gasoline in there, and you're getting go out of it. And then out of your tailpipe is coming what? Exhaust, a little bit of water, some pollution, right? All right. Now our continuous process, we want to keep in steady state, right? I think that's pretty self-explanatory. What happens if our continuous process is not in steady state? Remind me, what's steady state again? Benjamin, what's steady state? Right, when everything's balanced, right? So if my continuous process isn't balanced, what happens, Madison? It can blow up, right? That's the one I like. It either blows up or dries out, but I like saying it blows up. All right, so to do a balance on a continuous process, we're going to use what's called a differential balance. But don't be scared by the name. Basically, what it means is everything that goes in plus what we make in the process minus what comes out, minus what we consume in the process is going to equal what gets accumulated in the process. But what's really cool about a steady state is we can't be accumulating anything, right? Which means that what actually happens on the right side of that equation equals 0, which makes it really easy because then we can make it like this. Input plus generation equals output plus consumption. All right, so if I put 10 cookies into my body and I make 0 cookies while in my body, I should be gross, but I should poop out the amount of cookies that I ate, right? Make sense? All right, so let's go to the example on page 41. And this actually feeds into what Dr. St. Dennis was talking about earlier with environmental concerns. This is partly why environmental engineers will take this class as one of their first as well. We have real concerns for this, right? So a concentrated salt water solution is 50% salt water by mass and flows out of the factory at 50 kilograms per hour. However, before we can put that back into the ocean so we don't kill all the fish, we have to dilute it down so that it doesn't kill fish, right? It's not too concentrated. Okay? So what we're going to do to dilute it down is we're going to mix it with water. So the question I have for you guys is how much water do we have to mix it with? So in this case, we're not looking at what's in and out. We know what's coming in, we know what's going out, but now we need to figure out what else we have to add to it. Okay? So let me give you 2-3 minutes and take a stab at this one. Now let me point out one more thing before we get started. How many unknowns do we have in this example? 2? What are my unknowns? So, they're both labeled M, but they're on 2 different streams, right? So we have the total mass out, and we have the dilution water in. So how many equations do I need to come up with? How many? 2. I need at least 2 equations, right? All right, so let's take a couple minutes and solve this one. All right, we're running short on time. So all right, let's go ahead and do this one together again.
You can call it out. Joy talked too long.
No, that's actually not the case. Tonight's lab is really long, so I want to make sure you guys have enough time. All right, so what are we going to start with first? Benjamin, what are we starting with first? I'm picking on Benjamin all sorts of ways tonight, but what are we starting with first? No worries. All right, so first let's start with the salt component balance. Okay? So, is anything being generated? No. And is anything being consumed? No. So this very simply becomes in equals out. So we have a stream that's 0.4 weight percent times 50 kilograms. So how many kilograms of salt do we have? It's 20, which means that we have to have 20 kilograms of salt coming out. But we know that that salt has to be diluted, right? So that lets us solve for our unknown, which is m out, which then we can solve for by being 250 kilograms. All right, and that's just algebra, right? So we solved down for one unknown. And now we can go to the total mass balance, right? So if I go back to the picture and look at the picture, so now we know that we have 50 coming in, and we have how many coming out? How many? 250. So what do I have to have coming in? 200. All right, let's see if I did it right. 200, right? So what we did is we used the component balance to solve for one of our variables, and then we plugged that back into our other equation to solve for our total. So our overall answer is we have to mix 200 kilograms per hour of pure water with our salt process in order to not kill the fish. Okay? All right, now, so I know some people's heads are spinning, so let's dial it back a bit and let's talk about a mass balance that you guys are all quite familiar with. Well, at least those of you, I know some of you haven't done chemistry yet. But who can tell me what stoichiometry is? It's a nasty, horrible word. Yeah, fair enough. All right. Stoichiometry is just a mass balance, you guys. Right? All you're doing is you're accounting for the O's, the H's, the C's on one side of the equation and making sure that they match the H's, the O's, and the C's on the other side of the equation, right? You guys have already been doing mass balances in your chemistry. Right, so the stoichiometric equation we have up there is O2 plus 2H2 goes to 2 H2O's, right? Is that a balanced equation? Why? Yeah, it conserves what's on one side and the other side, right? So how many O's do I have on the left side? 2. How many H's do I have on the left side? 4. And how many H's do I have on the right side? Whoa, but hold on. There's different. That doesn't make sense. There's different things in front of the little things. There's numbers everywhere, right? All right, but yes. So we have 2 H2s, which is 4. We have 1 O2, which is 2 O's. And on the other side, we have 2 H2O's, so I have 2 O's and 4 H's. All right, you guys got it. Is there anybody who hasn't done stoichiometry before? Or at least gets it now, right? Anybody who doesn't get it now? Excellent.
It's like why you have to buy 3 bags of hot dog buns and 2 containers of hot dogs.
Drives me crazy.
To get the same number of hot dogs. Otherwise, you end up with either too many hot dog buns or too many hot dogs. It's really annoying. The hot dog manufacturers need to take stoichiometry.
Oh, I'm sure they collaborate.
One of you needs to go work for them and go fix them.
All right, so on page 42, consider the chemical reaction for the combustion of methane. Right? Combustion is burning in oxygen. Is this equation balanced? Daphne, is this guy balanced? What's that? Page 42. How many carbons do I have on the left side? You say it's balanced? Does anybody think it's unbalanced? Who thinks it's, so show of hands, who thinks it's balanced? Okay, so yeah, I think mostly balanced. So let's talk through it. How many C's do I have? C's what? Remind me. Carbon, thank you very much. Anybody know the molecular weight off the top of your head? Don't turn around and look at the periodic table. What's the molecular weight of carbon off the top of your head?
12.
Oh, very good. You guys will memorize carbon, hydrogen, oxygen, whether you want to or not. All right, so we have 1 C on each side. We have 4 H's on each side. We have 4 O's on each side, which means that we are balanced. All right, so let's talk about our engineering application real quick. So I want to talk about the fermentation of bioethanol. So I was actually talking earlier about brewing beer. It's actually the same process, except brewing beer is for drinking, and this is actually for making your cargo, right? But it's very fundamentally the same process. So what fermentation is at a very basic and funny level is you're putting a bunch of little yeasties in there, and they're going to eat the sugar, and they're going to fart out gas, and they're going to make alcohol. That's exactly what they do, right? There's no better way to say it. So what we're going to do, the equation is down here, right, is our glucose is C6H12O6, and it's going to break down into C2H5OH, which is ethanol. It's going to break down into 2 of those guys, as well as 2 CO2s, so you're going to make a little bit of gas, right? carbon dioxide gas. So the most common way to do this, like I said, is to put yeast and bacteria in there. So what we'll do is we'll take biomass, right? They'll take corn husks is a very common thing that they'll do, right? So we have a ton of corn that gets grown in the middle of this country. What they'll do is they'll take all those corn stalks, right? All you do is you eat that little yellow piece that comes out. Well, corn's like, what, 6 to 8 feet tall. You have all this green biomass. So what they'll do is they'll take it, they'll grind it up. It has some residual sugar in there. They'll throw it in water. They'll let it soak and kind of become this gross little stew. They'll throw the little beasties in there. The beasties will go eat it. They'll make a whole bunch of carbon dioxide gas, which is just fine in the atmosphere because we can deal with it. And then we have a whole bunch of ethanol, which we can then collect the ethanol, distill it down, and then we actually throw it in our gasoline as an additive, right? That's why when you guys go to the gasoline pump, for those who own cars, it says ethanol gas in it. But this is nothing more than a chemical engineering process. In fact, a lot of chemical engineers are employed at these type of companies. All right, so if we just break it down to what we've been looking at, what goes into our fermenter is sugar, water, and protein. And what comes out is ethanol, water, and proteins. And this is effectively nothing other than a materials balance problem. Okay, that's a very practical example. We could go into distillation of crude, and actually we will in a bit. So what I'd like to do before we take break, I want to discuss what we're going to do tonight for lab. I want to give you a little bit of background on it, and then we'll take a break, come back, and we'll get started. So pretty much the fundamental, well, really kind of the capstone where you drive to in chemical engineering is separations processes, right? So that's what we talked about. After, like what I was talking about in ethanol, we got this big nasty stew with the ethanol in there and a whole bunch of other gunk that we don't want. The question, and really the challenge for most chemical engineers, is how to get what we want out without getting the stuff that we don't want out, right? You don't want to be putting corn husk into your car tank, right?
And it's not just gas, right? It's in pharmaceuticals, right?
Absolutely.
Very rarely is there a drug that is made without something that they don't want, right? So it's everything. It's even in Coke, right? Even at the end of Coke, they're still figuring out how to filter out the last little bits.
Yep.
It's everything that is processed. How do you get out the stuff that you want without damaging it and remove the stuff that you don't want?
Yep, very well said. So what is a mixture? A mixture is a material made up of 2 or more different substances that are mixed but not combined chemically, right? And that's important because that means that we can do what? We can take them back apart, right? And that's our challenge, right? A good example would be like mud, right? What happens if you take like dirty lake water and you let it sit in a beaker for a long time? Mm-hmm. Yeah, it sinks to the bottom, but it might take a long time, right? So that's what, and actually mud is what's known as a suspension. So if we have a solution, like water, right, and we put little drops of dirt in there, or something like that, they will eventually, over time, fall to the bottom. But it might take a really long time to do that, and who wants to sit around, like let's say the zombie apocalypse has hit and we need to drink water. Are you going to go down to the lake, fill it up, and wait around 2 months? You are? Well, you're a dead man.
I'm going to use my life straw instead.
Right. All right. So a solution is a mixture of 2 or more substances that are in the same phase, right? So what we looked at before was where we had particles suspended in a liquid, right? So those guys are in different phase. We have a solid and a liquid. Those are significantly easier to separate because you can do what? You can use your life straw, which is filtering it out. You can also centrifuge it, right? Which is essentially just increasing the speed at which stuff sediments out. Okay, so that is one method of separation, but we're talking tonight about distillation, which involves solutions. So a good example of a solution is what we're going to be using tonight, which is Cherry 7-Up. Right, so this is water and sugar and some sugar and some sugar and some sugar, and there's actually some dissolved gas in there, which is what makes it all fizzy, right? So our objective this evening is we are going to turn this back into water. That's what we're going to be doing tonight. Okay? Now, in a mixture, the solute is dissolved into another substance known as a solvent. So the solvent in this is, does anybody know? Water. That's correct. And the solute is what's dissolved in there. Okay? So solutions are stable. Right? This guy, even if we leave it on the shelf for a long time, actually in this bottle it'll eventually lose its carbonation, but it will not separate. You won't get what we talked about earlier. You won't get the dirt at the bottom, okay? Unless somebody really screwed up and there is dirt in the bottom. But that would mean it's floating in there, okay? What we're going to do, and sorry, because they can't be separated over, because it won't sediment over time, what else we can't do? We cannot filter this. If you pour this through a filter, you will not get anything out of it. It will come through still as delicious cherry 7-Up, okay? So what we're going to do is we're going to use the principle of vapor pressures to accomplish what we need, okay? So at equilibrium, all liquids, and actually some solids, right? Like the desk technically has a vapor pressure, but it's pretty much unmeasurable. They have a number of molecules that are flying around above the air, right? That's why things evaporate over time, right? You have some amount of molecules that are at the surface. The wind blows it away. It has to repopulate that. The wind blows it away. It has to repopulate that. You lose your liquid water over time, right? But all different liquids have different amounts of vapor pressures. So we can use that to our advantage, right? So something with a low vapor pressure, like that vial there on the left, only has a couple of molecules flying around in the gas phase. Something with a high vapor pressure has a bunch flying around. And you can very easily conceptualize this when you guys go, again, to the gas station, right? You go to the gas station, what do you smell in the air? Gas, because gas is a highly volatile liquid, and that's why you smell it, right? There are other liquids, like mercury, that you don't smell because it has a very low vapor pressure, right? I don't know why you'd be in a situation where you're trying to smell mercury, but...
Yeah, don't do that.
Yeah, it's a bad idea. All right, so each of these guys individually, we get that low has very few molecules and high has a lot more molecules, right? But what happens if we mix them together? What we see is that each of those liquids still has a vapor pressure that matters, okay? So we still have some amount of blue flying around in the gas phase, and we still have some amount of red flying around in the gas phase, even though our mixture now is purple, right? We had a blue and we had a red, but our mixture is now purple there. We now have red and blue molecules individually flying around in the gas phase. So what we can do is we can take that gas phase and try to separate those molecules out. And how we're going to do that is through the process of distillation. So distillation is a process of separating components of a mixture through selective evaporation. The basic process involves heating a liquid such that the liquid molecules vaporize. Vapor is then collected, cooled, and recondensed. And if we do it just right, if we heat the mixture to just the right temperature, which is just below the boiling point of the least volatile chemical, what we can do is we can selectively get the majority of our product being one gas, right? Now, we all know that there's always some vapor pressure, so it's never going to be completely pure, which is why on some products you may see triple distilled, right? They're going to do it multiple times to try to do the process over and over again. So the process that you're going to be doing tonight is very simply drawn up here. What we're going to do is we're going to put our cherry 7-Up in a vial. We're going to add heat to it, which is going to cause it to do what? Start to vaporize. And then what's going to happen is that vapor is going to travel up the stem here, and it's going to collect into this guy, right? Because the vapor is going to go up, it's going to go anywhere it can go to collect into this guy, but now it's not being heated anymore, so what happens to it? It condenses, the drips go down, and we're going to collect in the distillate, okay? So the objective for tonight is for us to collect pure water out of our cherry 7-Up. Now, what do you also think is going to happen? What do you think will be left over in the distillation flask when we're done? Sugar? So, okay, let me ask this. What will happen to the color in your distillation flask as we do this properly? It'll be more clear in the flask?
In which flask?
Yeah. Sorry, in the boiling flask.
Yeah.
The stuff in the boiling flask, what's going to happen to it? It's going to get brighter, right? Because we're taking away the clear and we're leaving the colored, right? So if we're doing it right, we should see it get darker, and then we should see pure water come out on the end. Now, what you guys are going to smell immediately when you do this is the smell, because the artificial cherry flavor is almost immediately going to come off as soon as you start heating this, right? So you're going to get a quick burst of cherry smell, and then you shouldn't smell it. I mean, it'll still be in the room and prevalent, right? But you actually won't smell it because you'll drive that off very quickly, and then you're going to start getting your water out. Okay? So where this goes to in the engineering application is this is pretty much the target example of distillation, which is distillation of crude. So what they have here is we have this huge big behemoth, which is called a distillation column. And what they do is they put in hot crude and they continue to heat it. And what happens is that as the vapors go up, you can actually start collecting different weights of gases at different positions along the column. At the very top is stuff like heating and cooking fuel. And at the very bottom is stuff like tar that we use to make asphalt. And in the middle, you get different cuts of fuel, right? You get diesel, you get gasoline. You guys have seen when you go to the pump, you can choose between 3 different types, right? Those different cuts will come out at different points in the column. You can also get jet fuel, right? Different concentrations, all just depending on how we do the distillation process. Okay, but we're going to do it very simply, just with one. We're only going to take one cut, and we're going to be doing a batch process. Something like this is actually done continuous process, continuous feed, continuous output. Okay? All right, so at this point, do you have anything else to add, Dr. St. Dennis?
No.
Okay, so at this point, why don't you guys take your 5 minutes, we'll come back, and we'll get cracking.